under a curve. It's my favorite fake function, right? On an interval from A to B. Remember, when we're finding the area, we're chopping it up into an infinite number of rectangles. I made a finite. They each have a base of dx and a height, if I go between the x-axis, up on the function. All right, so all we need to do for our area is integrate base times height, and we'll get the volume. Keep in mind, though, a lot of times we're doing the area between two functions. So if it's just the area under this curve and above the x-axis, that's what we do. But if the functions intersect, like let's say that, and the top one is g of x, and let's call the bottom one h of x. And again, my area, drop this down. And I still need, this is a dx, I still need to integrate from intersection to intersection. Remember, sometimes with those, I'm going to call that A and B, depends on if your calculator active or not, how you find those intersections. If you don't have a calculator, you set the two equal, solve for x. If you do, you just calc intersect on your calculator. But now, because I have these two functions intersecting, like if this was the point 2, 3, and this down here was 2, -1, the height of the rectangle is 4. It's top minus bottom, or 3 minus -1. So we do top function minus bottom function. All right, there's no pies, there's no squaring or anything. It's just pure two-dimensional volumes, bases, and heights. Actually, I said that backwards, heights and bases. All right, so that's how we get the area of a shaded region. Next up, we have volume, but let's talk about volume by revolution, by revolving. And we did discs and we did washers, but we'll talk about both of them. You can see when I'm revolving here, I have circular cross sections. So let's just go over here. I'm just going to do a nice easy function for demonstration purposes. Let's do y equals the square root of x and x equals 4. And the x-axis, also known as y equals 0. So I have the intersection of those, right? And we're going to go generically first, but then specifically with this function. So you have to know what to revolve it around. I'm going to revolve it, let's say, around this horizontal line. In order for me to find the volume, I've got the pi because I've got the circles. Pi r squared is the area of the face. It's cross-section, and the area of this circle is pi r squared. Its depth is dx. So if I'm revolving, I draw my representative rectangle perpendicular to the axis of rotation. And when we did these, I said attach it with a little piece of string. Now, don't you put this on yours. If I was revolving around the x-axis, then this green, right, would be my radius, all right, and I just have a disk. All right, so we need to figure out the big R. Big R is from the axis to the outer edge of the curve. It's this purple distance. So for this one, my big R would be, I got to tell you what this is. Let's suppose this is a line y equals 5. Okay, my big R would be 5 minus 0, the bottom function. So my big R is 5. My little r is axis to the inner edge of the curve, top minus bottom. So my little r would be top 5 minus bottom. But in general, big R is always axis to outer edge, top minus bottom. Little r is always axis to inner edge, top minus bottom. So then we do pi times the integral from, and again, this is a dx problem. Whenever you go perpendicular to a horizontal line or revolve around a horizontal line, we do big R squared as a function of x minus little r squared as a function of x dx. So for this particular one, and we'd go across the x-axis, so I would go for this one, I'd go from 0 to 4. My big R, 5 minus 0 squared, minus my little r, 5 minus the square root of x squared dx. And then we'd either math 9 or integrate by hand. Now, if I had a dy problem, let's do that exact same one, but let's revolve it around a vertical axis. So let's take this yellow shaded and let's revolve it around the line x equals -1. So I'm going to whip it around here. I still draw my rectangle perpendicular to the axis of rotation. Because it's not touching it, little r won't be 0. This is now a dy problem. So when I integrate, okay, my big R is always equal to, I'm going to go purple here for big R like I did up there. Big R is always the axis to the outer edge. Right minus left. So the right function is 4. The left is -1. You can see that that length would be 5 because this is 1 and this piece is 4. But you really do right minus left. One of them is always the axis of rotation. In this case, it was the second one. In this case, it was the first one. One of them's always the axis, depending on which one's to be. Like if I had done my axis of rotation over here, then right would have been my axis. And whatever, you get it, right? So that's going to be a 5. My little r, let's be consistent. Maybe I'll do it in red. My little r is the axis. So I'm going to put my finger here for my stylus, and I go to the inner edge of the curve. I do right minus left. But now I need the x value here. And remember, this is y equals the square root of x. I need x. And x would equal y squared. So this is y squared comma y. If you don't get that, let's go put a point on here. 4 comma 2 is on that curve. You can see that the y is the square root of x, but you can also see that the x is the y squared. So we do right minus left. This would be y squared minus left, which would be the -1, or equivalently y squared plus 1. So when we set up our integral, we've got the pi, we've got big R squared minus little r squared dy. But you have to be careful because now we're doing this up the y-axis. So our limits go from 0 to 2, not 0 to 4. Okay, so just a little quick review. We are going to do volumes when we have known cross sections. Okay, so first of all, favorite fake function. Let's do that. 2 favorite fake functions. In this case, this is going to be the base of a solid. I will be building up off of it with cross sections that are either perpendicular to the x-axis, which we hope, we'll talk about that first, or if they say perpendicular to the y-axis, I would have gone like this. But once I go perpendicular to the x-axis, I like that because it's a dx problem. The general model for all area that you've ever done or volume, that you ever will do, is that you actually do the area of a face times, I'm even just going to leave it more geometric, area of a face times height. Like if you go back to geometry class, and your geometry teacher would have said, well, you have to do pi r squared. You got to get the area of this times h. That's the volume of a cylinder. Well, it's area times height. That's your 3 dimensions. All right. You might say I only see 2. Area is 2-dimensional, and then the height adds the 3rd. So for us in general, we are going to be integrating either left to right or bottom to top, depending on dx or dy. And then we do the area of a face, and then we give it its depth. And I'm going to do dx on this one. So the area of the face is sort of what you need to concern yourself about. So, and it depends whether you have squares. So let's go pop a purple square up off of here. If we do have this square, actually I'm going to make it look a little bit better here. Go a little slanted, I think. Let's go like that and like that. Get it look a little bit more like it's popping out of the paper. So if I were to make those and sweep them across the figure, I would need to add them all up, because it's like a loaf of bread and I'm serving you all up like a nice square piece. But for squares, we do side times side. So when we have a square, we're going to have the integral from a to b, side times side, dx. To get a side length, which would be this here in red, we're going to have to do top function minus bottom function. So point at that, and it's top function minus bottom function. Okay? If I did isosceles right triangles with the leg across the base, then this becomes a leg, this becomes a leg, and here's my isosceles right triangle with the leg across the base. So let's do that. And that would be the integral of side squared, but I'd have half of it. If the hypotenuse was across the base, if that was the hypotenuse, then the legs come up like this, and the multiplier for that, I haven't seen that one much, if at all, but just in case, when the hypotenuse is across the base, it gets shorter, so that's the one that has the 1/4 in front of it. The equilateral triangle, I'll put that on there too, but you don't see that very often either. I'll star the ones that are most common. We love the square. This one's pretty common. The equilateral triangles with 3/4 side squared dx. You do need to commit these to memory. The other one we see a lot is the semicircle. When we pop up off of these and we serve up those semicircular pieces. And for the semicircles, we do pi/8 side squared dx. Now again, if it was a dy problem, just before I quit here, if it was a dy problem and it's a perpendicular to the y-axis, we'd be going like this, and it'd become a dy. Our limits would go bottom to top, and then we would also have to solve our x's in terms of y. So like if one of them was y equals x cubed, we'd have to say, oh, we need x, maybe it's the right function to be the cubed root of y. So you just need to manipulate a little more in that case. And then the last thing I want to discuss with these, sometimes they'll tell you, it'll say that, like maybe this is a lake. And sometimes it'll say that the area of a face is given by 2x over the square root of x plus 3. They actually tell you that, so that all you need to do is integrate that. I'm making this up. Dx, because this already is the area, it already is 1, 2 dimensions. So if it's not a geometric figure that you know the shape of, they'll give you a model to use for the A. So it makes it actually easier, but it seems confusing because you're like, well, what happened to the squares? So remember, you have to do the area of a face and then give it its depth. Okay, so that's it for these. I'm going to stop sharing here. And let me know if you need anything. I'm always here. Send me an email if you need something.